Well, we're getting close to that time, aren't we?
All right, let me let me start the screen share, I guess. And I believe
I can introduce you and read your bio if you'd like.
sure.
All right. So welcome everybody. This is an intro to switch mode power supplies by Manuel Blanco. Did I say that right?
Yep, you got it right.
Awesome. He is a senior electrical design engineer at ITW, where he develops and directs new strategic project designs, initiatives, and market design requests that directly impacts his company's portfolio. He has a BS in physics from Seton Hall University and both a BS and MS in electrical engineering from NJIT. He's a senior member of the IEEE and active in its power electronics and industrial electronics societies.
All right. Thank you, Alex. And to
No
start
problem.
us off, I just want to welcome everyone to this seminar. Hopefully, those who are familiar with the art of switch mode power supplies will gain a more in-depth insight of what involves in it. And for those who don't know exactly what it is, it might incline you to maybe look closely at some of the products that are evolving in a broad spectrum of industries. And power supplies has been one of those things that typically was the last minute thought in a design process of a product. But ironically enough, it's the central functioning part of the product's device function. So with that, I'm going to talk a little bit about my background. Initially, most people that I know of that get into power supply design get into it almost by accident, or they happen to hear about it at some point in their career. I was fortunate enough that my dad was an electrical engineering technologist, mostly involved with radar systems design. And as a youngster, he got me heavily involved in all sorts of different projects, winding motors, and all sorts of crystal radios and RF and stuff. At that point in my life, I didn't really understand too much the theory of it, but I appreciated the end function of it. That piqued my curiosity, and fortunate enough to pursue it in college. Originally, my concentration was in communication systems, designing radar systems and things of that nature. While working in radar systems, I decided to go back and get my master's, and I started designing VLSI systems, again, for mobile telemetry devices like mobile phones and things of that nature. Initially started working at Digits. That was interesting there because I was developing the VLSI communication protocols and also the design features in these ICs that we were growing from ingots, actually, and basically doing device physics to, I call it bend gap engineering, because we were actually, from a chemical formulation coming up with the device physics characteristics and then making that fit a transceiver of sorts. Later on, I started working on the power supplies to energize that, and that's how I got involved with it by accident. Much later on, I started working at Avionic Instruments. There, most of my work there was involved with power inverters for commercial and military aircraft. What you see up there on the left are some of the mil standard chassis that run on 400 hertz to energize the cockpit pilot instrumentation clusters and also the accessory clusters on the commercial air flights. And much later on, I started working in LED light indication. Pretty much got into that industry also by creating switch mode power supplies to energize the LEDs in traffic lights and in hand and stop and crosswalk sign. But the clear thread on all these lapses that I've gone from industry to industry has been high frequency magnetics and power supply designs. And little did I know that it was the culmination of those two fields that are actually what make a good switch mode power supply design engineer. But as I started evolving in the industry, I sort of learned the process along the way. One of the things that I also do is I do consulting for a audio music store, actually 3 of them at this point, where I not only do I repair vacuum tube circuits But I also design vacuum tube amplifiers, acoustic amplifiers, and I'm extending that to implementing switch mode techniques into some of these devices that, ironically enough, are still used till today. A lot of people think vacuum tubes are obsolete, but in reality, they still use them in very high power tube transmissions, primarily what they call Tweed, which is traveling wave tubes, and also for X-ray tubes and medical diagnostic imaging. There's quite a few industries that still use tubes. Aviation, I believe most of the active warfare aircraft in the military use vacuum tubes because they can withstand nuclear blast and radiation. Unfortunately, the transistor cannot do that. And for semiconductor devices, you have to have them radiation hardened. And even then, their reliability at those power levels are not very reliant. So that brings me to where I am now in industry. I work for Simco Ion. Their primary devices that they develop there are for all sorts of conveying equipment, particularly in the electrostatic uh, technology. Typically, that involves heavy machinery, but we have different technical areas that we concentrate in, mostly conveyance and industry application specific areas where there's differentiated coulombic charges in a unit volume. And what they do is they create these electrostatic chargers or neutralizers, depending on the process that's being manufactured, to either eliminate electric charges or to make the product that's being manufactured safe, and also to keep the operators that overview the manufacturing of these products safe, because the voltage levels at those web speeds that are so high, they could really aggregate the charge quite heavily and create a spontaneous discharging, which can cause an explosion. But most of all, it could harm the human that's involved in the process. This is just an array of some of the products I've designed, and I wanted to convey particularly the size and the dimension of some of these power supplies, and how switch mode power supply techniques can be used to reduce primarily the size and the cost. That's really what we're after here. We're not, switch mode power supplies evolved based on that particular premise solely. Not to mention other factors like efficiency, but the cost and the size reduction and the weight reduction are quite significant when you operate transformer devices from standard like 60 hertz to something like 400 hertz, or a megahertz. Things become infinitesimally small in the switch mode power industry, and it's mostly driven by the high frequency techniques. As an example, on the top left there, you have what we call a ferroresonant transformer. Those are typical brute force lamination style transformers, and those that are familiar in that industry know that these devices are very bulky and heavy because they just use iron. And the weight and cost of the iron and the size is proportionally designed for the power level that you're delivering. Typically, these transformers don't store any energy, so in an ideal case, energy conservation is conserved from the input to the output because the device never stores energy. And I'll touch a little bit upon those dynamics once I get into the switch mode size. But just from a size perspective, you can see that the top left lamination transformer that operates in 60 hertz, for example, might weigh something like 8, 9 pounds and have a dimension of maybe 5 to 8 inches, square inches in volume, compared to the smaller switch mode type that I'm calling here integrated switch mode pulse type, basically about the size of a $50 or so. And you can actually get similar higher power and efficiency just by selecting the particular switch mode topology, the ferromagnetic material, and of course there's a science to how you wind and layer the wire in the core bobbin itself. So those are some of the intricacies that a switch mode power supply designer will have to balance. And you have to unfortunately build some of these things to get a feel for the magnitudes of those devices as you're building them. But you can drastically see the difference between the size just alone on frequency. These are just static applicators that these power supplies are being embedded into, which is something that we could not do with standard technology using, the lamination style transformers because they're just too big. But now with the reduction of the transformer being so small, operating at 50 to half a megahertz, you can get these things quite small and actually fit them in a really small confined space, which has led to the proliferation and development of new devices that have embedded switching. And that's kind of in line with Industry 4.0 because most of the industry now is moving towards more automation. And they're looking at these devices more like energy harvesters sometimes. And I'll touch upon that in a little bit. But yeah, so what I was saying in industry, most of the devices that we design at Simco have to do with contact friction separation. An example would be like the manufacturing of a paper bag or a plastic bag for that matter, that everyone's familiar with at a supermarket. When they get those bags in a in a processing field, they'll actually take the raw material comes in like a cylindrical drum in a web form about the width and height, I would say, of wherever you're located, 10 feet tall, and it's a cylinder. And as you can imagine, as they start unwinding this cylinder, it creates, in theory, a cylindrical capacitor that's been layered. And as they start unwebbing this and creating these different size bags and start adding different coloring and texture and all sorts of different features to the bag, you're creating a large amount of friction at a high rate of speed. So every time you have contact separation, there's a potential to have electrostatic fields build up and create explosions. I'm certain most people are from this demographic area. If you recall, I believe about a year or two ago, there was a big explosion at the Marcal toilet paper factory, believe it or not. What I just explained, the process right now in paper bag making can be extended theoretically to manufacturing toilet paper, which is a fibrous material that's layered on cylindrically. And if you don't have these static ionizers in the correct area, you can create a huge voltage gradient, which basically looks like a giant lightning bolt. When it goes off, it'll create a spontaneous spark. And if you have explosive sources close to the source, well, you can imagine how horrible that can easily become. So a lot of the miniaturization of this technology, at least for the stuff that we're developing here at Simco, has led itself to being able to monitor parameters that we couldn't monitor before, like voltage, amplitude, frequency, duty cycle, and we can actually contour the charge uh, with these miniature power supplies to get them to operate in a certain way for a particular um, process. And we call that like a static formula or formulation of sorts that we help our customers with. So that's led to, like I mentioned, a lot of the monitoring equipment that we also manufacture to give the customers some idea of, like, if their efficiency is up to par with their process, and when the equipment needs servicing or cleaning. So those are just some of the areas that we've been able to explore on a macro level for customers. And all this stuff is very much, and we have several patents on this. In fact, I'm working on one right now, to be able to control the dynamics of charge, voltage, frequency, and conduction angle, to come up with these elaborate formulations for particular processes. This is another example of a product that I recently designed a couple of years ago. You can see at the bottom left there, the transformer is almost the size of a silver dollar. And this particular power supply, when it's all put together, it's almost like the size of an iPhone, if you think about it. And remarkably, this can take 24 volts DC and create 30,000 volts at 1 milliamp. So you can get 30 watts of power in that. So those are the type of things that we've been able to do with the high frequency switching techniques that is afforded to us with switch mode power supplies. And again, I was touching upon how these things are becoming so small. We can embed these things into applicators. This is a particular applicator called a neutralizing bar, where we have all the electronics completely embedded in the applicator itself. So there aren't any tangibles like wall warts or wall plugins that you need to reduce voltage from the line frequency to 24 volts to drive this. You just need to feed this DC, and there's enough smarts in this thing, um, and a switchable power supply in it, that it'll just create 30,000 volts, or you can even scale that as required. So with that, I want to start talking about what these switch mode power supplies are. Now that you kind of have an idea of the size, domain, and how these things can be miniaturized. Switch mode power supply is exactly as the name calls it. It's a power supply that's switchable at different frequencies, unlike standard power supplies, which we are typically familiar with, that switch at a single frequency, like line frequency, 60 hertz in the US and 50 hertz in Europe. But power electronics was not really defined as a particular area of study. It kind of borrowed different elements from different areas to formulate what we call today power electronics. But just to give you a historical background of where its origins began, slightly after Faraday discovered the law of induction, basically with his electromagnet experiment with the compass needle, because back in the 1800s, the mid 1800s, they were enamored with how can you create electricity from magnetics, and magnetics and electromagnetic magnets as well. So the theory of magnetism and electricity were not coinciding. They were just beginning to become interleaved theoretically back in those days. They were thinking that magnets operated a certain way and electricity operated in a slightly different way. And it wasn't until Michael Faraday did his experiment of electrical induction with the compass, and then Maxwell's equations came into play. But the real guy that did the most of the work that we still use today, almost 200 years later, was Nikola Tesla, which he was able to create an electrical grid as we know it today, using transformer action from Faraday's law of induction and implementing it into a commercial device we call a transformer now. But originally, power conversion back in those days was done in what I call a very brute force method. You either had DC machines, DC rotating machines, or AC machines. And if you were to create a conversion, for example, from AC to DC, you would actually take a DC dynamo and couple the axis of that dynamo to an AC generator. And you'd have two rotating machines coupled on the axis. And that's how you would do your brute force power conversion. Much later on, when rectifiers and the early beginnings of actually just before vacuum tubes took off, they were making DC using like gas discharge tubes. They would actually take a vessel and it would be filled with mercury. They would actually heat the mercury to a certain temperature. And when the mercury, obviously through heating effects, depleted, it would only conduct in one direction. So that's how they were able to replace the DC component of the conversion by using mercury gas discharge tubes around 1900 or so, about 50 years later. And then, somewhere in the mid 1930s or the 1920s, actually, vacuum tubes came into play, but they were too slow for anything practical in switching techniques. So there was a period of about, I want to say 30 or 40 years where power electronics was not even a phrase back then. It was more or less power engineering, and people associated that with heavy power equipment, transformers and generators, never anything that was tangible like a small product, certainly not an electronic product. Obviously, late in the mid 50s to 60s, with the advent of the of the transistor being invented not far from here in the 1947 in Murray Hill, Bell Labs. That's where power electronics really got a huge catapult. And because we had already gained knowledge about how diodes work, how Fleming's triode work, and things started really coming together from a circuit point of view. And obviously that led to more integrated designs in the late 70s with the first integrated, dedicated IC for switch mode power electronics made by Unitrode in 1976. So you can get a feel historically how the field started out kind of snailing along, and then vacuum tubes brought it to the next level, and then transistors obviously catapulted it to what it is today. These are some of the first consumer products that implemented switch mode power supplies. The first computer was an Apple II. That's a kind of an internal picture of it. And the HP 35 calculator was the first one that had a self-driven switch mode power supply that utilized semiconductors in it. And that was around the 1970s, mid 70s, sort of. As I was explaining earlier, power conversion or power, typically for us electrical engineers, that usually means heavy power. We're talking tension lines and heavy power equipment. That's what we normally gravitate to when we hear, oh, you're in the power business. But now power conversion has taken a different form. As I mentioned before, most of us got into this field by accident, including myself. But this kind of gives you an idea of where power electronics is right now and why it took a while. Actually, it wasn't really formulated into a field until the, I want to say, 1975 or so. And it originated as a field actually in Caltech. It was only two universities that were actually specializing in power electronics, Caltech and Duke. Now I think University of Colorado and other universities have implemented their own power electronics curriculums, and now they're calling it, I think they're calling it energy, smart energy these days, or energy conversion, or energy management, or new energy protocols. But the reason why power electronics had kind of like an unconventional dynamic in its start is because it borrows from three independent fields that typically electrical engineers concentrate on one specific field. And those fields are system and controls. Now, when we're designing a switch mode power supply, you don't have to be a control systems expert, but you have to put that power supply in some sort of perpetual check mode so that it's converging on both voltage and current. So in order to know if the power supply is stable, if it can handle the load, the dynamic load process of it, you need to know something about control systems and how filters work, because now you're using a duty cycle controlled pulse width modulation, which is almost like a communications transmission technique to excite a very small transformer to get some signal synthesis out of it. And you have to filter that somehow. So obviously, when we look at the design of the magnetics and how to control this device, there's going to be some things that have to that coalesce with communication systems. In fact, if you drive the frequency beyond a megahertz or so, something simple like a two-winding inductor doesn't start quite behaving like a two-winding inductor as you would think it would behave. So you have to have that paradigm of the equation. The other side of it is you have to know analog and digital circuit design, because now you're going to be designing a control system for controllability from observability, but now you have to implement the physical devices that are going to do that with different topologies. And some of these topologies I'm going to discuss a little later on are going to determine the actual function of the supply, whether you're stepping up, stepping down in voltage, or you're doing both, or if you're going to switch it, if you're not going to step up or step down voltage, if all you're doing is operating at a different frequency. For example, power supplies that typically work in ships and in aviation equipment operate at 400 hertz. You still need 120 volts, but it's not at 60 hertz anymore. It's at 400 hertz. So you have to know something about magnetics. So and also about thermodynamics, because you have to also keep in mind that these switching devices, although from a theoretical ideal point of view, they're not uh, they're supposed to be lossless. They're not. They have parasitic capacitances, which create signal delays in the switching. They also store energy, and some of those energies could be parasitic, not only to the switching function of the power supply, but also to the switching dynamics to get the output that you require. And the other component of it is power and energy in the traditional sense. You're going to be connecting this to different drives, loads, and energy processing equipment. These days, everything's going electric. I think there's a huge, just like there was a big campaign to eliminate incandescent filament bulbs a couple of years ago, and I think they're becoming scarce, very scarce to find these days. Um, there's going to be I think I read somewhere recently that by 2040 or something like that, um, internal combustion engines are going to be obsolete in the car industry, in the transportation industry. So that's why there's a huge opportunity right now for anyone that's studying electrical engineering, to really have a grasp and a hold of these three areas, because uh, you could pretty much write your own ticket at this point, because you can work solely just on the communication protocol of it, the actual magnetics, or the energy processing of it. And what's driving that really is the electric car and the electrical transportation, as we migrate away from fossil fuel dependency. And that's a really good thing. There's also energy harvesting that's coming along for the ride with this, because a lot of this energy right now can be reused. So I think we as a society are becoming more conscientious about the wasteful amount of energy, and basically taking care of our planet as we move forward. Um, Historically, the first converter that was created, I believe, was the flyback converter. Its origins, ironically, started uh, in the automotive industry. This gentleman here, Mr. Kettering, he developed two key inventions during that time for General Motors. One of them was the starter motor. Um, Basically, in those days, if you had to get your Model T started, you would actually have to insert a crank in the front of the engine and turn this crank, which was wound by a heavy helical spring. And a lot of people broke their arms and got really hurt, because once you wound this crank that was purely mechanical, if you let go of it at the wrong time, there was no catch spring. So if you stood in the way of it, there would be so much torque generated, people would get hurt. So he came up with an ingenious way to make this starter motor to be able to start these engines without the dangers of turning this crank. The other thing that Mr. Kettering did is the first inductive discharge system in automobiles, and that's really where the origins of the flyback converter comes from. Those who are familiar with old CRT technology know that, or even televisions that use CRT, know that the flyback transformer is at the heart of creating the image on the picture tube. Now, the reason why it got the name of flyback for that application was because the horizontal screen, as it tracked from one side to the other, actually flew back across the screen very fast. And then the voltage that was needed to develop on the anode for the acceleration of the electron gun inside the tube required a high voltage gradient, something in the orders of 20 to 30 kV, depending on the size of the screen. For the automotive application, basically there was a distributor system here. There's two coils here that are basically acting like a auto transformer, and they're basically doing the boost application. When we say in power electronics that we're boosting, it means that we're taking a lower voltage and creating a much larger one. In this case, the 12-volt battery on the automobile is auto transform boosted to something like 5,000 volts to be able to generate a voltage at the spark plug, such that when the piston reaches its top dead center, you can have compression and an explosion, and then obviously capitalize on that on the power stroke to drive the drivetrain and get you accelerated and such. But you can see here the very basics of at least a flyback system, and I believe this patent was from 1912. So historically, you can see that electricity, magnetism, two separate fields up until 1850, Faraday's experiment, and then later on with Maxwell's proofs, brought those two together. And then it was just waiting for the technology to sort of evolve to be able to implement these theoretical things to what we have today. Um, so power conversion can be classified in power electronics as a processing of power. Typically, we don't consume power. We actually utilize the devices that consume the power for our application. But there's a classification that identifies the function that the switch mode power supply is performing based on the input and output voltage parameters. If we're taking direct current, which would be akin to something like a 9-volt battery or a 1.4 DC battery, if we're taking a DC source and making it an AC source, we call that process inversion or just inverter. If we're taking an AC alternating current and converting it to another AC alternating current at a different frequency or voltage level, we call that a cycloconversion. And if we're taking a alternating current to DC current, we call that process rectification. And then there's some devices that require DC to DC conversion. Since we're taking one DC source and essentially converting it to another DC source, we just call that a converter. But to give you an idea of all the practical aspects of a switch mode power supply, we have an interesting system up here where the sun, the solar array collects sun during the sunny days and stores that in a battery. We take that battery, which is a purely DC system, we connect the switch mode power supply to that, and we convert it back to AC so that we can sell it back to the grid. Or in our case, if we want to plug our cell phone to the wall, we can actually use that inverted process at this point to convert the AC back to DC to be able to charge our smartphone. In a similar process, an example of DC to DC conversion would be the car charger for your phone, where your smartphone works on like 3.3 volts and the car battery is on 12 volts. So obviously there's a mismatch in voltage and current there. So these little devices that are smart but portable chargers do the power conversion for us. And you can see, I don't know if you've ever taken the time to look at the small print in there, but some of them are pretty heavy. Some of them generate 3 amps. And this is about the size of a small can of mints or something like that. So it's pretty impressive that you can get that type of volume in such a small space to charge your cell phone or your tablet. But you can see the thread on how we typically use switch mode power conversion devices all the time flawlessly without realizing that we are using this stuff. When we're actually designing the switch mode power supplies, there's a few elements that as power converters engineers that we typically use. We use inductors, obviously, to be able to couple 2 coils and store energy in them, and then transfer the stored energy to either a higher or a lower voltage using a transformer device. And then we use a capacitor basically to move that charge depending on how much current we need. So we use the inductors essentially to get the voltage level that we want. And we use the capacitors to store that charge in some form of energy so that we could deliver it to the load. And the transformer is nothing more than an extension of 2 inductors coupled by magnetic material that lets us flawlessly either elevate the voltage or the current depending on the duty cycle. And then obviously we need some switches in order to perform the switching aspect of this. And then diodes to rectify in the case that we're making DC. Typically, we do not use resistors because if you try to use resistors to reduce voltage, you find out that their efficiency is not that very great and you do not get enough power out of them. They're only very good for very small things. But we do use them in the discrete sense to make the feedback control systems and other ancillary circuits to support the switch mode power supply. Now, the reason why we use inductors and capacitors is because their average product is 0 for the switching cycle. So, for example, in the middle here, you have the DC component, which is 0 for the PWM circuit. But what we do is when we turn on the inductor for a particular time period, we store energy in that inductor. And then when we shut it off, we make sure that we time it appropriately so that there's never any energy stored in the inductor. The same energy that you store, you release. So the average aggregate of the energy in the inductor product is 0. So essentially, in theory, the inductor won't dissipate energy, but because a physical wire has inherent resistance in it, it will heat up. So this is a theoretical level that you'll get to 0, but not exactly 0. There's some losses there. And the same thing with a capacitor. We use the capacitor to store energy in what we called a charge second balance, where the energy and charge that we put in the capacitor is equal to the same amount of energy algebraically when we get it out. So in theory, the product of that average is 0. So essentially, in theory, they're lossless. A more clear example of that would be a switch. I know we use transistors and such, but think about this open switch. And if you have a voltage source connected to that, obviously if the switch is open and you connect the voltmeter to that, you'll measure the full voltage across the switch. But since there's no current being passed, the product of voltage times current when the switch is open is 0. So it's not going to dissipate any heat. The same can be said when you close that switch, and now the voltage becomes 0 because essentially is a dead short, but the current elevates exponentially. So again, the product of voltage times current for the switch becomes theoretically 0. For the PWM that we use, what we do is we take that switch and we turn it on for what we call a duty cycle. So if the switch is completely turned off, that's called 0 duty cycle. If it's completely turned on, it's called 100% duty cycle. If it spends half of its life on and off, we call that 50% duty cycle. So essentially the time that the switch is on can be from 0 to 100, and we vary that pulse width modulation with frequency control. And we use that frequency control to work the applied voltage onto the inductor or the capacitor to move the charge over. And since the aggregate is 0, the average, when you take the Fourier transform of the periodic signal, you get the average of the applied voltage across there based on the duty cycle controlled voltage that you feed the transformer for the application. Here's an example of a lamination transformer. It's not a switching power supply. This is what we call a linear power supply. It takes an input voltage, 120 volts, 60 hertz, lamination transformer, and then it creates this rectifier arrangement here, which we call full bridge. And you can see the process of taking an AC signal, down converting it with a transformer, and then rectifying it to create DC. It's kind of like an evolutionary. It's not a switch mode power supply in the high frequency sense because the frequency here is 60 hertz, but it gives you kind of a feel for the elements of how the voltage and current are being controlled to change from one type of voltage and current to another. Now I mentioned before that the arrangement of the switch, symbolically represented by a transistor here, the diode and the inductor and the capacitor, the particular arrangement of those three items as we use the power conversion is what creates the topology. So when we do a bucking process, we're taking an input voltage and reducing it even more than the input voltage. So that's called a bucking process. If we take the input voltage and make it much higher than the input voltage at the output, we call that a boosting process. So this is a typical buck boost topology. And then sometimes there's applications when we want to do both. Like if you're driving a servo motor that needs a specific speed. So you can look at this as not just a power supply, but also speed control. For example, on an electric vehicle where you hit the accelerator, in cases that you want to accelerate and go fast or decelerate and go slow, you would use something like a buck boost topology there to be able to either increase or decrease the voltage at the output based on the 12 volts that's typically used on a DC system. These are called non-isolated converters. But you can see if you add another coil in parallel, in the case of the buck boost, if you add two coils in parallel, which is the coupled inductor winding on the right, you could do that with a transformer, a one-to-one transformer. And then since you have galvanic isolation, now you can separate primary from secondary, and that's your flyback converter. So the dynamic here in the flyback converter is you can arrange this to get a much higher elevated voltage, which is the typical topology that we use on many products that I've been designing these days, with 24 volts in, and then have it scaled anywhere between, let's say, a kilovolt to 30 or 100,000 volts. So in essence, the takeaway from here is fundamentally there's three components: transistors, inductors, coupled inductors as transformers, and diodes. And the arrangement of these things are called a topology, depending on what type of conversion process you want. Focusing more on the transformer, because it's not just creating an inductor, you have to look at the intricacies of the magnetics of the transformer. Here I'm showing a BH loop of a push-pull type of configuration, where we're using the top right first quadrant and the bottom left third quadrant. And we're able to either compress this BH loop or elongate it depending on the frequency of operation. And if you integrate the area inside that's covered between these two loops, that's called the power loss in the core of the transformer. So as a switch mode power supply designer, it's not just creating this product or device that elevates or reduces the voltage and the current, but you also have to see how these devices are behaving amongst themselves, because you don't want to do that process and waste a lot of energy in doing that, because now then you're going to be handling a thermal problem. So, you have to be aware and use Faraday's law of induction to find out, how much magnetic permeability you need for the core based on the power volume that you require. So here are two equations that typically are used in the design of this. And that's what really governs the size and the weight of these transformers, even though they're small. Depending on how much power you're going to feed your load will govern how much window area you're required to do that. This is just the tip. The other side of it is also the winding laws. Here I show different styles of winding. You could layer in the center of the page, you could layer the winding one on top of each other, kind of in between the progressive wind, or you could separate the one. A lot of the intricacies involved in the winding has to do with leakage inductances, because you don't want a lot of leakage in your transformer because it'll build up as heat. And as I said before, the heat's got to go somewhere. So if it's not being efficiently used and transformed into your load, then that's something that you're going to have to delegate with in your design. Again, up here at the very top, these particular configurations, the buck for reducing, the boost for elevating, and the buck boost does both, are called fundamentally the basic topologies. In the middle of the page are more elaborate derivatives of the buck boost or buck boost in what we call the forward, flyback, and push-pull. Honestly, these topologies keep evolving depending on the application. I think at the moment there's probably about 12 different types of topologies. Some of them are more complex, some of them are more conducive to certain applications, but fundamentally they all find their root application and theory in either a buck boost or a buck boost. They're all derived type of converters. So then you might be asking yourself, well, how do I know which converter to use? The first thing to ask yourself is, do you need isolation? If you don't need isolation, then you can use one of the three basic ones. If you do, then typically the topology selected by the power level, something like a 2 kilowatt power supply may require like a full bridge versus something like a flyback, just because of the voltage and current levels are just not being very well delegated in the flyback topology. So typically efficiency, relative cost, performance, and the application, but mostly it's the losses in some of these devices to help you do the power conversion that you really have to juggle. From a commercial point of view, well, that's all the stuff from the design aspect of it. But from a commercial point of view, if you're going to have this product marketed and it's going to be used by consumers, you're going to want to have this have some sort of compliance regulatory markings, and that's going to require you to, have some idea of magnetic interference, communication systems, and a lot of that stuff is really related to where this product is going to be used. If you're going to be using it for medical applications, which is one of the harshest ones to test for, or if you're just using it as an ancillary secondary support device, or if it's just going to be a commercial non-life bearing operation. But you've probably seen a lot of these regulatory symbols on products that you've seen these days. This is a typical electromagnetic compatibility testing chamber. Basically, it almost looks like you're in a different planet. You put your device on what they call a plenum table, and they'll basically exercise this device with all sorts of different tests: harmonic, static discharge, flicker, surge. And it's the reason why they do a lot of this compliant testing that you can see some of these devices that you use, for example, like your phone charger, that it could withstand a blackout and it doesn't destroy the device, or you can plug other devices into it that are in the standard of the USB plug and play charging protocol. But they do a lot of these elaborate testing just to make sure that you're not destroying the device that it's being intended to be used, but most importantly, that you're not polluting the AC going to other devices in your house or in neighboring areas. So those are typical tests that they perform on all those products. I touched upon this before. Robert Romano in '76, working for Unitrode, at the time Silicon General, he was the first guy that was able to create an integrated IC, because as I will show in the next slides, although power electronics had evolved by the 1970s to be able to create these devices like the Apple II that I showed, the open chassis, the sub functions to create a switch mode power supply never were all coalesced into a microchip until 1976. So in other words, if you had to create a pulse width modulation, you'd have to create that function. If you wanted to create a feedback control system, you'd have to create that function. These sub functions were separate and analog, and they were never integrated. So you can imagine the level of complexity to get all these items to work together into a functional power supply. You almost have to be like a systems engineer almost to get these things to harmoniously work together. But that was it. And then one of the industrial type of products that used this particular IC was the teletype machine. You know, that was able to capitalize on some. And I think they were under a contract, Unitrode, to create a power supply for these teletype machines back in the '70s, which is what accelerated their interest in culminating these things to being much smaller and integrated. I touched upon this just slightly, but this gives you pretty much the fundamental items that you need to create a switch mode power supply. You need an error amplifier. In this particular chip, it has two. It has they're undedicated, so you're going to need an error amplifier to make sure that your power supply is regulating the output voltage to a reference, and you're also going to need one for current mode compensation. So that's why they give you two here. You also need an oscillator that's programmable. Typical oscillators are ramp generated to generate a pulse width signal that's like a square wave. That's a function that has a duty cycle that's variable from 0 to 100%. So it's just kind of nice that you can make this into an integrated circuit and just add two elements, an R and a C, and create a product of that to create the frequency generation portion of it. You're going to need dead time comparator. The reason why you need dead time comparator is for certain push-pull topologies that use two magnetic coils. You can't have the coils on at the same time because you create punch through and a dead short, and you'll either damage the transistor or create some other ancillary condition. So that's why you have to have this dead time control here, and that's very easily variable depending on the application. And you also need a D flip-flop. In the case of the simple topology ones that use one switch, you can just use a single Q output. But if you're doing quadrant 1 and quadrant 3 switching across that BH loop, you're going to need two switches to do that operate 180 degrees apart and that don't have any overlap time when they switch due to this dead time comparator. So in essence, this is one of the most primitive chips from the Unitrode family. It's still being used today, ironically. If you ever are amused to crack open a power supply for a computer, uh, I think 90% of the power supplies in that use a form of this particular chip to generate, obviously the switch mode power supplies in some of these computers go up to 2 kilowatts, I think, for some of these heavy application loaded towers, data towers and servers. Here's a small schematic of a power supply that generates high voltage.
Can I cut in real quick? Sorry.
Sure.
We're coming up on the end of the time soon. So I was wondering if we could leave a little time for questions soon.
Oh, yeah, sure. Let me wrap this up real quick. This particular schematic has all the elements that I just touched upon: the transformer, the PWM converter, feedback circuitry, transformer, and transistor switch. One of the things I wanted to get into real quick is how some of these things, for me actually, because I'm involved in a lot of audio design, how to implement switch mode power supplies for vacuum tube technology, particularly guitar amplifiers and things of that nature. So typical tube designs have 2 transformers in them, one for the speaker and one for the power. These are the brute force lamination ones. You can see that the cost of this is like $265 for a mono block, weighs 16 pounds, and works on 60 hertz. So what I wanted to show here is how you can go from something that's $90 that weighs 9 pounds for a 50-watt amp. You can create this little breadboard that I created here as a buck operation to get 60 watts, more power than this guy, and in such a small space. And it only weighs 7/10 of a pound versus 9 pounds. So you can clearly see from a topographical point of view the huge benefits that you get from making switch mode power supplies. And this is just, I used that same chip I told you before in the bucking operation. These are just some quick calculations that I did. I did it for both 20 kilohertz and 45 kilohertz operation frequency. The takeaway there is as the frequency goes up, the inductance value goes down, and the input voltage goes up as the value of the inductance goes up. So that's all related to the charge balance and the inductor balance that I spoke about. These are the load graphs of that particular power supply, the steady state load graphs. You can see it's pulling 6 amps. And these are the actual product or the actual test fixture that I did in the lab. These are the waveforms that I showed you before theoretically. You can see that this square wave, this has a shorter on time than an off time, and that's the duty cycle control. You can see the inductor trapezoid on top that follows. And these are the efficiency measurements. Those are actual scope measurements from the theoretical. And this is just a prototype that I've been working on. You can see the benefits of that. For those that are interested in more theory, these are some of the books that I've been reading throughout my career. They're mostly theory. And if you want to do more practical building, these books here are pretty good and pretty much state of the art these days. And these are more additional power supply practicing type of books. And with that, if anybody has any questions about anything, I know it's a lot of heavy theory. I really tried to keep it in sort of layman terms so that anyone can grasp some of these theories and fundamentals.
Thank you very much.
Oh, great. My pleasure.
If anyone has any questions, feel free to unmute or type them in the chat.
Hi, I'm one of the co-hosts for today's event, and I was just gonna ask. I remember you asking about physics, and I remember you saying that you have a degree in physics and both electrical engineering, I believe. How did you feel about the transition between learning both?
Actually, that's a very good question. Back when I graduated high school, I originally wanted to go to NJIT. I got accepted to NJIT. I got put on the waiting list for one semester. The interesting there is I got early acceptance into Seton Hall. So I went there just by pure luck. I said, okay, rather than taking the summer off, I'll go early. I'll take early summer classes at Seton Hall. Well, it turns out that the classes that I took there, um, I met with my presumed to be advisor in the physics group, and he took a liking to me. I took a class with him. It was an intro to physics class, and he really was the one that was recruiting me into that particular field. I originally just wanted to go straight into electrical engineering, and I had expressed to him, my advisor at the time, that my plan was to transfer to NJIT. And he told me, he's like, listen, I want you to keep thought of something. And I didn't know this at the time. And this, unfortunately, this degree program is not really well publicized by the university. I still don't know why this day. But anyways, I had learned through him that that Seton Hall University has a dual degree program with NJIT, where the kicker is you go to Seton Hall for 4 years, and during that period of time you acquire a degree in physics from Seton Hall, and the last 2 years you get an engineering degree from NJIT in any discipline that you want, whether it's chemical, civil, electrical. I chose electrical just because as a kid I that was like my hobby. I built stuff with my dad and stuff like that. So that really, I gave that some thought, honestly. And I said to myself, well, if I go to a regular engineering school and I graduate in 4 years, I'm just going to have an electrical engineering degree and nothing else. But if I can knock this out in 4 years, I'll have both a physics degree and an electrical engineering degree. And during that time, robotics and mechatronics was not a field yet, as we know it now. So I figured, hey, this is a great way to marry mechanics and robotics with the physics element of it, and bridge it with electrical engineering, and I can pursue that. And I basically chose the field that way, based on that unique offering from the university, a dual degree program. And it worked out really well because honestly, a lot of the theory that I learned in magnetics and device physics from Seton Hall, and electrostatics, electrodynamics, all of the things that fall under the physics paradigm were repeated. And actually, when I went to NJIT to finish my electrical engineering component of it, I found that that was more of a review of stuff that I already knew. For example, Ohm's law is nothing more than a remanifestation of F equals ma in physics. Instead of using a physical force that we measure in pounds and a mass that we call current, and an acceleration we call voltage. It was kind of an interesting paradigm for me to be able to, it wasn't like I was learning something new is what I'm trying to say. It was very much a review, and I just had to learn for the electrical aspect of it, the nomenclature of the language, more or less. So it really worked out really well for me. And that led me to pursue a master's at NJIT in communication systems. But there's people that are involved now in physics that have the physics background alone, but because you get the exposure of the mathematics and high level type of thinking in the realm of physics, because when you do a physics program, you're going to cover chemistry 1, chemistry 2, electrochemistry, electricity, magnetism, intro to electronics. You're going to cover, and even software programming now. I think a language is a requirement now. It really lended itself very well. So that's why I said in my case, it almost happened by accident. But I was glad that my advisor took the time to explain that to me. And I wasn't aware of that program when I went to Seton Hall. I kind of discovered it, or it discovered me, more or less. But it really helps you out. It really did in my case.
Yeah, that sounds like it turned out really awesome for you. So that's awesome. That's good to know. Thank you so much.
Yeah, and the one thing that I wanted to do a lot more of was actually programming. But the little programming that I did, because most engineers take some sort of language. At the time that I took it, it was C, embedded C. I think now there's more exotic programs out there like Perl. Arduino wasn't a thing when I was back in those days. So if you wanted to do any type of development work, you really had to buy the development kits, and they were very expensive and kind of out of the reach of the standard hobbyist or the person that was interested. But now with the proliferation of so many kits, and now you can take these kits and program them in Perl, MATLAB, all sorts of different languages now, Ruby. It's almost like the language barrier of it. You pick a programming language that you're very comfortable with and start programming that way. And for the most part, most of these languages, at least from software perspective, they really are very similar in many ways. Some of them have shortcuts based on the semantics of the language, but for the most part, they all do the same sort of thing: data storage, data acquirement, and processing. So if I know, Alex, you were looking into being in power systems, and I don't want you to be discouraged, because when I was an undergrad as a double E, when I heard power systems, immediately I thought, okay, it's going to be high tension wires, power plants, nuclear plants. And that's what I thought, because I didn't have anyone to really talk to me about, oh, wait a minute, power systems is not just huge power. It's also these smaller things called switch mode power supplies that coalesce, magnetics, high frequency communications, and all these other different elements. I feel like, once you get out there in your career, you're going to find a niche area that you're going to work in. And it's not that you forget some of this theory, but because you're not exposed to it, you tend to not be as comfortable with it. And I find that power electronics is one of these areas where it keeps you quite active in all these other sub elements, because it really brings them and binds them together as a uniform field, actually, for energy harvesting or any of these things. Now with a lot of the movement right now and a lot of the talk now is energy harvesting, solar, how to go green, especially the transportation now with everything becoming electric vehicles. We're really pushing the envelope on that side. And I think we're really, it used to be power electronics was just topologies, magnetics, and controls. Now we're pushing the envelope to looking at new switching techniques, new switching methods, not necessarily switching at gigahertz speeds or something like that. Maybe switching at 60 kilohertz, but being able to implement new switching technologies and methods. Now the talk of devices is gallium nitride, silicon carbide. Those things are really opening the door for some really unprecedented things. Like you can have like a 50 kilowatt car charger in your house. And what's really driving this is, even though they're pushing the electric vehicles so much, there's really no electrical grid infrastructure to support that. So we're almost kind of snailing along, pushing the state of the art with switch mode power techniques to be able to bring that to a consumable usage paradigm, so that it doesn't, cripple the grid. And even the grid is getting some substantial notice these days with things going on in Texas now.
We'll have to move. We'll have to go to the other to the other presenter for the keynote. You have brought us to the cutting edge of technology, and we're really grateful. It's been a fabulous ride.
Okay, great. If anyone has any other questions, you can certainly reach out to me by email. I'm on LinkedIn. So if
Would you like to put your email address in the chat, or if you wish, only if you wish, because then it'll be recorded, or you have it. You can show it somewhere.
Oh, you have it. Okay, yeah, sure, that's fine. And like I said, moving in the future, I plan on making some kits and stuff, so that if anyone is further interested in exploring some of these things on their own, that'll be exciting as well.
Fantastic. All right.
Well, thank you very much for having me.
Alex, you want to say anything else for your part?
I was just going to say thanks so much for presenting. Very interesting presentation. Your presentation actually concludes track 7 for today. So like Aaron was saying before, if you're interested, head on over to the keynote speaker.
Got a minute to get there.
Yeah, but thanks again.
All right,
I really enjoyed it.
Oh, great. I'm glad to hear that positive feedback. Thank you so much. And everyone enjoy the keynote speaker. I'll see you there. Thank you.
Thank you.
Thank you.
All right. So I think that went pretty well.
Oh, yes, it did. And even somebody who's totally untechnical like as I am, was able to pick up things. And I was just reading about PSE&G, which is making a very big push for the electric vehicles, and also investment companies, which are making enormous contributions to develop that part of the storage of the energy. So, well,
Oh,
I better
yeah,
let you
yeah.
go. I better let you go, because otherwise you
All
won't
right.
be able to. You're gonna
I
miss
hear
the
you.
keynote.
And Alex, I know that you're in the field now, but if you have any questions, feel free to reach out to me via LinkedIn or whatever. I know that you said that you were thinking of concentrating in that. Believe me, I hope I touched on some areas that
You did,
maybe you can
especially toward the
appreciate.
end there.
Oh, good, good.
But
I'm
thank
glad.
you so much. I will definitely look out for you on LinkedIn.
Okay, great meeting everyone. I'll see you at the
right.
keynote.
Thank
See
you.
you at the
Have a good
keynote.
one.
Thank you.
See you. Bye-bye.